All right. Shh. Lesson 10.5, comparing linear, quadratic, and exponential models. All right. Well, how I'm going to start out is just with simple graphs of each of these functions. So the first graph is a linear function, okay? And what do we know about a linear function? Well, it rises at a constant rate, right? We know it's got a constant rate of change. That's why it's got a straight line. It's got some slope to it, right? Okay. Then the next is a quadratic function. And if we take a look at our quadratic function, we see that it's a parabola. And that's pretty interesting. We learned that it's got a vertex, it's got an axis of symmetry. And we know that it goes up according to the square of x, right? It's 0 squared is 0, 1 squared is 1, 2 squared is 4. And so if we take a look at this, if we take a look closely, and I want to show you guys this, I want you to be able to witness this. If we take a look closely, we see that the linear function actually starts off growing faster than the quadratic function. The quadratic function has a smaller slope. It's not growing as fast until it gets to this point here, right here, 1, 1, 1, and then our quadratic function starts growing faster. You see, and then if I really zoom out, you notice that it becomes incomparable, right? The quadratic function starts growing much faster than the linear function. You guys see that? Okay. So those are those functions. And then we have our good friend exponential function. And here's our exponential function. And it looks a little bit different. I'd like to compare for a second, and I'm actually going to do 2x minus 1 so they all start at the same place. Okay? So here's our exponential function. And I'm going to get rid of our linear function just so you can see this. Look, initially, if you take a look, initially, our quadratic function is growing slower than our exponential function. You see that? Our exponential function is actually growing faster in the beginning. You see that? The exponential function is red. Okay? So our quadratic function is growing faster. But as we go out, we notice, look what happens. You see this? Here's our red exponential function. Over time, the exponential function starts growing faster and faster. And if we take a look, we see that it then surpasses our quadratic function. Can you guys see that? Is that pretty clear? So again, our quadratic function starts our quadratic function is initially growing faster than our exponential function, but as time goes on, and if I make my x-axis a little bit smaller, we can see that our quadratic function outpaces our exponential function outpaces the quadratic function. You see that? So if I put my linear function back on there, here's my linear function. Obviously, it grows much slower than our quadratic, but then our quadratic function grows much slower than our exponential in the long run. You see that? So that's just a kind of comparison of exponential, quadratic, and linear functions and how they look. Is that pretty clear? It's cool. So that's a visual insight. But now let's delve a little bit deeper. Let's say I start with our simple linear function, f of x equals x. If I wanted to graph this function, I would say x, f of x, 0, 1, 2, 3, 4, 5. Okay? And if I find my function, I just plug it in. It's 0, 1, 2, 3, 4, 5. Good? Okay? And we can notice that it's going up at a constant rate, right? It's going up by 1 each time. And how I can show this is if I find the difference between the two terms. The difference is 1. Then 2 minus 1 is 1. then 3 minus 2 is 1, then 4 minus 3 is 1, and 5 minus 4 is 1. Okay? And so the difference between each following point is constant. You see that? This first difference, this difference is constant. You see that? Between the 2 points. That makes sense? And that's true no matter what linear function I have. Okay? So another linear function I could say is just f of x equals 2x. So 0, 1, 2, 3, 4, 5. Okay. And this would be 0, 1 is 2, plug in 2 for x, it's 4, 2 times 3 is 6, 2 times 4 is 8, and 2 times 5 is 10. And these go up by 2 each time. You see? So the first difference is constant. Does that make sense to you guys? Okay, that's pretty obvious. All right, so we can move on. Now, if it was negative 3x, it would be going down 3. The difference would be negative 3 each time. Does that make sense? Okay. But let's get into something a little bit more new. What about f of x equals x squared? I said x, f of x, 0, 1, 2, 3, 4, 5. Okay. If I plug in 0, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Now, if I look at this, they're definitely not going up at a constant rate, right? Okay. And I can see that by finding the difference. Well, the difference between this one, 1 minus 0 is 1, 4 minus 1 is 3, 9 minus 4 is 5, 16 minus 9 is 7, 25 minus 16 is 9. But wait a second. Do you guys see the pattern? The first difference is not constant, but what about the second difference? 3 minus 1 is 2, 5 minus 3 is 2, 7 minus 5 is 2, and 9 minus 7 is 2. Oh, that's pretty cool. So the first difference isn't constant, but for a quadratic function, the second difference is constant. You see that? That's pretty cool. Let's show another one just to make sure we're not just bluffing here. F of x equals 2x squared. X f of x, 0, 1, 2, 3, 4, 5. 0, plug in 0, I get 0. 1, I get 2. 2 squared is 4 times 2 is 8. 3 squared is 9 times 2 is 18. 4 squared is 16 times 2 is 32. 5 squared is 25 times 2 is 50. Okay, find the first difference. It's 2. 8 minus 2 is 6. 18 minus 8 is 10. 32 minus 18 is 14. 50 minus 32 is 18. Okay, that's cool. So the first difference isn't constant, but look, 6 minus 2 is 4. 10 minus 6 is 4. 14 minus 10 is 4. And 18 minus 14 is 4. That's pretty cool. You see? So that's interesting. But I want to take it one step further, okay? So this is all according to the lesson because we've only learned about linear, quadratic, and exponential. But I want to show you guys something, if you will allow me. So we know about x, that's linear functions, x squared, that's quadratic functions. The second difference is constant. But what about a cubic function? X, f of x. 0, 1, 2, 3, 4, 5. 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. Okay. Is the first difference constant, class? First difference, is that constant? No? Yes? No? Doesn't look like it. 1 minus 0 is 1, 8 minus 1 is 7, 27 minus 8 is 19. 64 minus 27 is 37. 125 minus 64 is 61. Okay, well that's definitely not constant. Let's try the second difference. 7 minus 1 is 6. 19 minus 7 is 12. 37 minus 19 is 18. 61 minus 37 is 24. That's not constant either. but maybe you guys see the pattern. 12 minus 6 is 6. 18 minus 12 is 6. 24 minus 18 is 6. It's pretty cool, right? Yeah, I just realized I was like, that's, wow, whoa, yeah. Okay, so I just erase that number from the board. No, we don't have to live in fear. So that's pretty cool. Look, guys, look at what? That's crazy. Amen. What about x to the fourth? So look, x to the 1, the first difference is constant. X to the 2, the second difference is constant. X to the 3, the third difference is constant. Guys, what about x to the 4th? What? X to the 5th, the 5th. What? This is crazy. Are you guys with me? Are you seeing this? That's cool. That is interesting. It just blows my mind sometimes. Now, that's great. I like that. Okay, so we learned something today. That's cool. All right. Now let's go on to the final one, which is exponential functions. F of x equals 2 to the x. Okay. So x, f of x, 0, 1, 2, 3, 4, 5. Plug in 0, this is 1, 1 is 2, this is 4, 8, 16, 32. Now in this case, I'm not going to find the differences because the differences, it won't work. It doesn't work in the same way, so I'm not going to go through that. But how does it work? It doesn't work with differences, it works with ratios. 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 8 is 2. 32 divided by 16 is 2. You guys see that? Okay, is that pretty clear? So with exponential functions, it's not the difference, it's the ratio. Okay? And that's exactly what exponential functions do. Remember, we learned doubles every time. That's, or triples every time. Or if I did 1/2 to the x, it's taken half every time, right? Okay, is that pretty clear? All right. Well, those are all characteristics of these functions: linear, quadratic, and exponential functions. Okay? So that's basically it for today. So let's give an example of what I'm talking about. Okay, what is the actual type of question that you will see? What's an actual type of question that you will see? Hold on, let me find it really quick. This one here. Everybody turn to page 495 in your books. Page 495 in your books gives you a table of values. And with this table of values, it says, tell me what function, what kind of function this is. That would give me this kind of table of values. Okay? And so we would go ahead and look at this and we'd say, all right, well, how do I figure this out? Well, I find the first differences, the second differences, and the ratios. All right? So the first difference is quite easy. Do 3.5 minus 4 is negative 0.5. Then 2 minus 3.5 is negative 1.5. Negative 0.5 minus 2 is negative 2.5. Negative 4 minus negative 0.5 is negative 3.5. And negative 8.5 minus 4 is negative 4.5. A lot of you guys can probably already see a pattern there. But that's how we find our first difference. Now, first question, is the first difference constant? Is that constant? No, it's not. It's not constant. If it was constant, those all would have to be the same number. First difference is not constant, which means it's not what type of function? Not necessarily constant. It's not a linear function. Yeah, close though. Good. It's not a linear function. So the first difference will be linear. If this is constant, it'll be a linear function. So then I tried the second difference. Negative 1.5 minus 0.5 is negative 1. Negative 2.5 minus negative 1.5 is negative 1. Negative 3.5 minus negative 2.5 is negative 1. Negative 4.5 minus negative 3.5 is negative 1. You see? So the second difference is constant, which means it is what type of function? Quadratic. And we don't have to check the ratio because we already know that it is a quadratic function. But we could check the ratio, and how would we do that? Well, we would divide the numbers instead of taking the difference. So you do 3.5 divided by 4, and you obviously need a calculator, is 0.875. 2 divided by 3.5 is 0.57. And honestly, we can stop there because are those ratios the same? No, so it's not a quadratic function, but just so we can get practice. Negative 0.5 divided by 2 is negative 0.25. Negative 4 divided by negative 2 is, or negative 0.5, sorry, is 8. And negative 8.5 divided by negative 4 is 2.125.
Do I have to leave my Chromebook in here?
Anybody see a Chromebook? Is that where you sit?
Yeah.
Okay, cool. All right.
All right,
Good.
thank you.
You're welcome, sir. All right, so is the ratio constant, guys?
No.
No, so it's not what kind of function? If the ratio was constant, it would be an exponential function. You see?
If they're all the same, that's what type of.
Yep. If they're all the same, that's what type of function it is.
What if they're all the same?
It's impossible.
That's a mathematical possibility.
Maybe it is possible, but I don't know of how that would be possible.
So what would this one would be quadratic?
So what type of function is this?
Quadratic.
Quadratic. Now, class, just to check, we plot it. So negative 2 to 4, 0, 3.5, 2, 2, 4, negative 0.5, 6, negative 4. And we can't tell because, interestingly enough, we can't really tell here. This might be an exponential function by that shape, right? It could be potentially an exponential function, but that's why it's important to do this table, you see? Because with the graph, we wouldn't be able to tell. But with those first and second differences, we are able to tell that that is, in fact, a quadratic function. You see? Does that make sense? Cool. Now, an obvious question or a logical question is, how would this apply in the real world? Well, imagine if you are working at the CDC, the Center for Disease Control, right? And you're tracking like influenza or something. And you notice in a city that influenza is increasing, right? And it started out as 100 cases, and now it's 300 cases, and then it's 700 cases, and then it's 1,500 cases, and whatever. And you've got this data, and you're noticing this growth, right? And you're looking at that and you're trying to determine what type of growth is it. Is it linear growth, which means it's growing at a constant rate, and in which case you don't have to be too worried? Is it quadratic growth where it's growing at this x squared rate? In that case, you kind of are pretty worried because that can get pretty fast pretty soon. Or is it exponential growth where it's like literally doubling every week or something? In that case, you definitely have to be worried because that obviously can skyrocket pretty quickly. You see? And so you might have a determination like, you know, the flu is going to have an outbreak all over the country during flu season, But you might see, okay, it's growing linearly here, not a big deal. It's growing exponentially here. We need to put our resources here to make sure we're getting quarantined and putting our resources there to spend our money in that place. Does that make sense to you guys? So that could be a potentially real life situation where you'd want to know what type of growth you're experiencing, what type of function you have. You see? And you would only have data points. You wouldn't have like, oh, the f of x equals 3x to the what. You're not going to have that. You're just going to have data points, and you're going to have to determine what kind of function you're seeing. You see? Is that clear?
Yeah.
Okay. So that's a kind of real-world application for that. With that said, that's basically it. Your homework. Your homework is on. Oh, I skipped it, didn't I? 504. Is that where it is?
Yep.
Thank you. 504, numbers 1 through 8. Okay? And you're basically doing exactly what I just did. Okay? You don't have to worry about like end behavior and all that kind of stuff. Just don't worry about end behavior. Okay? Just focus on first difference, second difference ratio and graphing the function, okay? And you have to tell me what type of function it is after you complete that plot. Does that make sense? Any questions? Okay. Homework is page 504. Numbers 1 through 8. Any questions? Okay, good. Good job, class.